Okay, so next topic is Ohm's law. Ohm's law is the current flowing through a conductor is directly proportional to the voltage applied across it, provided the temperature okay provided the temperature and other physical quantities remain constant. Remains constant. Sarah, here, just look here, I is equal to NEVDA. In these is N, that is the number of charge carriers in a conductor. Can you count the number of charge carriers in a conductor with your naked eye without using any instrument, without using any special instrument? No. What about the drift velocity? We also cannot find the drift velocity. But how about the area? Area, we can observe using our naked eye, right? We have an idea about what is area. So here, this area is a macroscopic property. Macroscopic means you can just look at it using a naked eye, or you can understand it. Just like pressure, temperature, all of them, you can feel it by yourself without any special instrument. So those are macroscopic. When we say microscopic, we will need special instruments, or we are not able to straight away find the value. Okay, so here, this current I, how about this current I? This current I depends on area also. Area is a macroscopic property. So current becomes a macroscopic property. Got it? Because you can measure current. But when it comes to current density, look at current density. If you want to find current density, you need to know N, E, and VD. All of them are microscopic. So here, current density is a microscopic quantity. So current, we use current. So the current, we can straight away find current. But current density, we need current density when we deal with something at microscopic level. For example, we will study about transistors. Nowadays, transistors have become very, very small, that they are almost the size of 9 atoms. So there, we are not going to have large current. We are going to have small current. That current depends on very few quantities like this. Got it? So that's why we need the idea of current density. Noted? Sarah, have you noted? Okay, so from this, we have V is proportional to I. So this is the law. V is proportional to I. To make this into an equation, we introduce the constant R. V is equal Ri. But we used to use this as V is equal IR, rearranged. So what is R? R is the resistance. So here R is a constant. Where R is a constant. What is R? R is the resistance. So we can tell that R is the obstruction to the flow of electric current. To the flow of electric current. This is known as, or it is known as resistance. Okay. Note, note number one, V is equal R into I. So if I draw a graph, this is in the form Y is equal to mx. Y is equal to mx. So here, the graph is a graph that goes through the origin. This is I and this is V. Here the gradient M is equal to R. If we plot V is equal Ri, then I is equal 1 over R into V. Now we have Y is equal mx plus C again. Sorry, not mx plus C, mx. This time also we have a similar graph. Independent variable is V and dependent is I. This is the graph. Gradient is equal to 1 over R. So be careful about the question. In MCQs, you might get both these graphs, VI or IV. So depending on that, the gradient changes. As resistance or 1 over R, we call this as conductance. Okay. Once you have noted, let me know. If you have noted, let me know. Saja, noted. Not yet. Note number 2. Conductors that obey conductors that obey Ohm's law Ohm's law are called are called ohmic conductors, and others others are called non-ohmic conductors. Conductors that obey Ohm's law are called ohmic conductors, and others are called non-ohmic conductors. Okay. Not really. Note number 3. Let's say we have a resistor, positive, negative. Current flows in this direction and resistance is R. Now, if I change the direction, the current will flow in the opposite direction. The resistance is R. If we plot the graph, so we will have a graph like this. It will be a straight line, okay? It's a straight line that will go through the origin. So why did it go to the negative side? We have changed the direction. When we change the direction also, it is still a straight line. So this is an ohmic conductor. Why this is ohmic? Because here, look, V is proportional to I. If V is proportional to I, it will be a straight line as well as it will pass through the origin. In your OLs, you might have studied about the diode. It will let current flow in one direction, but it won't allow current in the opposite direction. This side, current is equal to 0. So, uh, when I plot this graph, when I plot we get a graph like this. Here, do you find V proportional to I relationship in this graph? Do you find V proportional to I relationship? No. Therefore, what type of conductor is this? Is this not a conductor? Is this ohmic or non-ohmic? This is non-ohmic. Non-ohmic. V not proportional to I. Therefore, this is non-ohmic. Sarah, did you get it? So this is tungsten. Initially, let's give positive to this and negative to this, and negative to this and positive to this. So now, if I plot the V versus I graph, make a change. This is I, this is V. Make the change. This is V, this is I. Done. Okay. So now we have a tungsten bulb. If we plot the V versus I, uh, when voltage increase, the current flow through this will increase. then this will heat up. When this heats up, resistance increases. Therefore, current will gradually decrease. So our graph will look something like this. When I increase, or when temperature increase, resistance increase. So here, what is M? M is equal, V equal IR, right? V is equal IR. I is in the y-axis, therefore I is equal 1 over R into V, therefore M is 1 over R. So when temperature increase, resistance increase, therefore gradient decrease. So look, the gradient is decreasing. What can you tell about this graph? Is this ohmic or non-ohmic? Is this ohmic or non-ohmic? So this is non-ohmic. Sarah, here the graph is going through the origin, but is V proportional to I? If V is proportional to I, we get a straight line, but this time we get a curve. Therefore, it's non-ohmic. Got it? So mention V not proportional, V not proportional, V not proportional to I. Okay, noted. Next, we have semiconductors. So as I mentioned, in semiconductors, when we increase the temperature, when we increase the voltage, current increase, temperature increase. So we'll understand it later. For now, when temperature increase, current increases in semiconductors. So if you plot V versus I, semiconductors, we get a graph like this. V is equal IR, I is equal 1 over R into V. So here M is 1 over R. When temperature increase, resistance decrease. Okay, here resistance is decreasing, therefore gradient is increasing. So what can you tell about this semiconductors? What can you tell about semiconductors? Ohmic or non-ohmic? Okay, clear. Now let's draw the V versus I for a practical conductor. So normally a conductor, the V versus I graph is like this. V versus I graph is just like this. So here, what can I tell about this region? In this region, we observe that V is proportional to I, right? Look, it's a straight line. It is going through the origin. Therefore, V is proportional to I. But here, it is not. So I can call this region as ohmic region. Ohmic region. This is non-ohmic region. So here, V not proportional to I. V equal IR volts. That means we can use V equal IR. So don't confuse between Ohm's law and V equal IR. Ohm's law is V proportional to I. This equation you can use in ohmic region as well as non-ohmic region. But in non-ohmic region, when V changes, I changes, R changes, the resistance changes. But in ohmic region, resistance is constant. Is that idea clear? So during your order, you might be thinking that V equal IR is the Ohm's law, but it is not. Okay. Here, in this, resistance is not constant. Resistance is not constant. So, so up to this, is it clear?